So this video is going to talk about generators, AC and DC, and this is in chapters 32.6 and 32.7 of the textbook. Okay, so remember from the last video we talked about Faraday's law and induced EMF, and we saw that if you had a changing magnetic flux, you induced an EMF. So you can use that to build a generator. So imagine, like in the picture here on the right, so imagine you have some coil of wire and you just rotate that. So by rotating it, well, then if you have a constant magnetic field, well, the relative direction of the field and the loop are changing, so that dot product when you calculate the flux is changing, so you induce an EMF. So you have an induced EMF, and then, well, if we attach this to a circuit, say a light bulb or something, we'll actually get an induced current. Now, if your coil is rotating at a constant angular velocity, then the EMF you induce is going to be sinusoidal. And in fact, this is how you build an AC generator. And in fact, pretty much every power plant at some level is based on rotating a coil of wire to generate an EMF. So, well, of course, typically it's many coils of wire, but the whole idea is, right, so you're doing something, whether it's a wind or falling water or a steam turbine. So you're doing some mechanical work to rotate this thing and you're generating an EMF, so electrical energy. And then, of course, an AC generator in reverse is really just an AC motor. So to derive some equations that we can use for generators, so if you have a rotating coil and a constant magnetic field, the EMF that gets induced, well, it's the number of coils you have times the magnitude of your magnetic field times the area of the coils times omega, where omega is the angular velocity that you're rotating the coil at, times the sine of omega t. So this is the sinusoid part. So you can think of this as a max EMF times sine omega t. And then if you hook that up to a circuit with some resistance, you can get this expression, the second expression here for the current. So if you have an AC generator, well, of course, it's just a sinusoidal thing. So the average EMF and current is going to be zero. So it's useful to define something called the RMS, or the root mean square average. So basically, to get the RMS, you square things, right? So you square it, then take the average, then take the square root. And what happens then mathematically is this turns out to be the maximum over the square root of 2. And again, this is just a way to take the average, since if you just average out a sinusoid, just a simple average, you just get 0. So in the US, so the power in your house, so the RMS EMF is 120 volts with a frequency of 60 hertz. Whereas in Europe, they use an RMS EMF of 240 volts and a frequency of 50 hertz. And you can also talk about power. So the average power is equal to the RMS current times the RMS voltage, or again, each of those brings in a square root of 2 compared to the maximum. So that's a half times the maximum power, Imax times the max RMS, or max EMF. So you can also build a disk generator. So one way to do that is with Faraday's disk generator. So basically, if you have a big circular conductor, so you rotate it and you put a magnetic field into one part. So of course, then in the conductor are charges. Those charges are going to feel a force. So they'll actually drift in one direction. And if you're turning this thing at a constant speed, then you're going to get a constant EMF. So something else you can do, so we talked about an AC generator. So we talked about split ring commutators back when we talked about DC motors, but you can add a split ring commutator to an AC generator and you can actually flip the sign of one of the cycles. So you don't actually get a nice constant voltage, but you get something that's always positive or always negative, depending on how you attach it. So the EMF is always in one direction, but it's not constant, although there's other stuff you can do to the circuit to make it look more constant.